So let's now start talking about how exactly we can reconstruct phylogenetic trees from molecular data. In this course, we will touch on many different methods: parsimony, likelihood, Bayesian methods, and distance-based methods. The first one we will touch upon is maximum parsimony, mostly because it's historically one of the oldest methods and also because it's fairly simple to understand and explain. So what is maximum parsimony? Well, as I say, when we look at molecular data, the homologous characters we use to infer phylogenetic trees are columns in an alignment. So let's now walk through an example with this very small example alignment. We have 4 species, A, B, C, and D. We have an alignment with only 3 positions in it, columns 1, 2, and 3. If we start looking at column 1, then we will notice that A and B both have a G at this position, while species C and D both have a T. The simplest explanation for this data, the simplest explanation is that A and B are more closely related to each other, or shown as a tree like this. A and B are grouped together in the tree, C and D are grouped together in the tree. This is actually the parsimony criterion. Parsimony means choose the simplest possible hypothesis. If you have some data and you have a set of alternative hypotheses explaining the data, then you might as well choose the simplest hypothesis that's consistent with the data. There's no reason to choose a more complicated hypothesis if a simpler one fits the data well. That is what the parsimony criterion is. So under the parsimony criterion, looking at this one nucleotide position, we would place species A and B together, since they both share a G at this position. Based on that, we can actually also do a parsimonious reconstruction of the evolutionary history. Since C and D have a T, and since A and B have a G, there must have been a change at some point in the evolutionary history. We can infer that maybe it was on this internal branch in the tree. The ancestor here had a T, this ancestor had a T. On this branch, the T mutated to a G. That ancestor then had a G, and both A and B then inherited that G from their common ancestor. The alternative, if we instead assumed that A and C were together, for instance, would amount to homoplasy. Okay? We would now have A and B at 2 separate locations in the tree. They would both have a G, the other species would have a T. So we would now, instead of assuming that they both inherited the G from the common ancestor, we would now have to assume that they evolved the G independently, like indicated at the bottom slide here. It would be the same situation in the third possible tree, namely where we put A together with D instead of A together with C. It's entirely the same situation. A and B are apart, and we have to assume that the G's evolved independently, that they were a homoplasy. So when we look at just this one character in the alignment, assuming that homoplasy does not occur is the same as finding the shortest tree. The shortest tree meaning the tree requiring the fewest mutations. On this tree, where we assume they inherited the G from a common ancestor, we require just 1 mutation. On the bottom tree, where we assume that they are not together, where we assume that the G's evolved independently, that it's a homoplasy, we instead require 2 separate mutations. So assuming no homoplasy is the same as looking for the shortest tree. Those 2 things are entirely equivalent. So let's see what happens if we look at nucleotide position 3. Again, we can see that species A and B have a G in common. So again, the simplest explanation is that they are together in the tree like before, and that they inherited that G from the common ancestor, and that there was a single mutation in the evolutionary history. If we combine positions 1 and 2, we can see they both agree on the best tree. It's this one where A and B is together. Both of them, there's no homoplasy. Both of them require a single mutation on this branch. So for both positions, we require 2 mutations in all. But how about if we look at the at the second nucleotide position, the last nucleotide position here? This is different. If you look carefully, you can see that in this case, A and C share the same nucleotide. They both have a G at this location. So if we look only at this nucleotide position, then the bottom tree is in fact the most parsimonious. We would have to assume that A and C are together on the tree, that they both inherited that G from the common ancestor, and that the history requires just a single mutation. If we tried to put nucleotide position 2 on the tree that we've been preferring up to now, we instead have to assume that A and C, which are now separate, have evolved their Gs separately, that they are homoplasies. So it's a conflict, okay? The second nucleotide position is most consistent with the bottom tree and inconsistent with the top tree. The two other positions are more consistent with the top tree and are inconsistent with the bottom tree. If we put them on the bottom tree, you can see both first and third positions in the nucleotide, both nucleotide positions 1 and 3, would require us to assume that these A and B characters evolved as homoplasies. They evolved independently. So we have a conflict. How do we resolve it? Well, we do it simply by all in all choosing the shortest tree. All in all, the best tree is the top tree, okay? The top tree was consistent with positions 1 and 2. If we place all the different mutations on that tree, we can see it requires a total of 4 mutations. A and C, the positions 1 and 3 were entirely homologous. That worked nicely. Only the single position was in conflict and required an assumption of homoplasy. So one assumption of homoplasy on these 2 branches and the other 2 sites were okay. Gives us a total of 4 mutations. If we instead try to place all the sequences on the bottom tree, we would need more mutations. In this case, the central nucleotide position is evolving okay as homology, but now both positions 1 and 3 require a homoplasy and will therefore require 2 mutation seeds. So all in all, top tree requires 4 mutations, bottom tree requires bottom tree requires 5. We prefer the shorter tree, which is equivalent to assuming that homoplasy is rare. So we would rather assume 1 homoplasy than 2 homoplasies. That's the parsimony criterion here. And that's entirely equivalent, as I say, to finding the shortest tree. If we can find the tree that requires the fewest mutations, then that is the most parsimonious tree. Under maximum parsimony, therefore, the best tree is the shortest tree, the tree requiring the smallest number of mutational events. That tree is the one that implies the least amount of homoplasy, the fewest least amount of convergent evolution, the fewest reversals. But the question is, of course, how do we actually find that tree for any given data set? On this particular data set, we could do it by hand. What if we have a real alignment?